Swayam Prabha. Digital India. Educated India.
Hello, welcome to this session. In the previous session, we looked at clock buffer, or you can say CMOS clock buffer, where we buffered the oscillator output coming from the oscillator using an inverter like this, and then connected here. We chose an optimum value of the capacitor CAC, which is the AC coupling cap, and this was connected to VDD. Okay, this out is the output of the oscillator, and this is clock. So, now if you think about it, you will get the desired clock. The buffers will add some amount of noise. Now, this particular inverter, when you are doing a power optimized design, this particular inverter which you are seeing here, this inverter is conducting current, is always conducting current actually, okay, because your gate and drain are shorted. So, both PMOS and NMOS, they are always conducting. So, sometimes it happens that this inverter has a lot of power or current consumption. Okay. So, because this inverter has a lot of current consumption, there are two alternatives. Okay. One of the alternative is that in place of using this inverter connected back to back, you connect that using a large resistor. Okay. So, let me just draw it a little more clearly. So, you have a resistor like this. Well, this is connected to VDD and this is connected to ground, and this is RF. So, when you connect a resistor in feedback across the inverter, you input and output. This inverter is going to be biased for sure like this. Okay. So, it is going to be biased like this. So, PMOS and NMOS, they are still conducting current always, and they are biased in saturation. Your DC operating point is such a way that this potential V in and V out, they both are same. Okay. So, with this feedback resistor, the thing which changes here is that because you are having a resistor, large resistor here. So, when you are going to connect your oscillator with this load, so you have an oscillator, and when you connect this particular inverter, so you have an AC coupling cap like this. We have chosen the AC coupling cap in such a way that at our frequency of oscillation, this AC coupling cap acts like a shot. Okay. So, for the frequency of the oscillator, acts like a shot. So, you are loading your oscillator with this particular buffer. This is the buffer now, right. So, when you load it, the current which is going into this load will be minimized, because the impedance is earlier, the impedance in this case which is seen by your oscillator is 1 by GMP plus GMN plus S, whatever the parasitic capacitance. Now, in that impedance you get feedback resistor, okay, which increases the impedance seen from here, because it increases the impedance. So, the current drawn from the oscillator, the current which is drawn from the oscillator, I can call this as IL. This current will depend on the impedance seen, and if you are loading with a very low impedance, that means a lot of current will go in driving that, right, and it is also going to change the output frequency. Ideally, if I say that the looking in the buffer case, the looking in impedance ZL tends to be infinity, right, then your buffer will not actually load your, you are loading your system with infinite impedance, it is not going to change the frequency, it is not going to take any current from the oscillator. But when you are loading with the self biased inverter in this manner, you have a low loading which draws current from the oscillator and changes the output frequency. So, to increase that impedance, we actually introduce this resistor RF. The current consumed within the inverter still remains the same as it was. So, there were couple of problems as I told. One thing is the current which is consumed in this buffer, and this still remains the same. We have not yet tried to address that. The thing which we address is the current drawn by the buffer from the oscillator, okay. And in the same way you can also say the frequency changes in the oscillator because of the buffer. Those two things are minimized. The second option which we have, or which you can utilize, you want to bias this node, or you can say you want, because I am following up my the self biased inverter with inverters to amplify the signal, right. So, somehow I need to get this voltage here, which is the same voltage as we get for the self bias inverter, but I do not want to consume a lot of current by connecting in this manner. Okay. So, how to do that? Another option which we have is the following. So, in place of, so let us say when I had this inverter connected in this manner like this, right, I assume that this is VDD, this is 0, and this potential happens to be VDD by 2. The current which is consumed will depend on your gate overdrive and threshold voltages, right. So, I change my top and bottom branch, or you can say I stop this inverter itself in such a way that if I use two cascodes here, or you can say if I increase the length of this device both NMOS and PMOS, then the power consumption is going to be lesser. So, what I do is increasing the length is typically same as this. So, in place of using the self bias inverter as shown on the left, I go and use the inverter as shown to you on the right. Okay. So, if I do this, then I can very well design this circuit such a way this voltage is also VDD by 2. The current consumption in this circuit, so if I call this as current I1, the current which is flowing here is I1 and the current which is flowing here is I2, your I2 is surely less than I1. I am using the same MOSFETs, let us say WP by L and WN by L. So, this is WP by L, size is the same. So, if I do this, then the I2 current is going to be lesser. So, you can reduce the current consumption in the self bias inverter, but all other inverters which you are seeing here, all these inverters are going to be same as simple single inverter, not, we are not going to do anything to that. Okay. There is a trade off in doing this, right. The trade off in doing this is that when you connected more devices at the gate node, the parasitic capacitance increases. You are having double the length. So, surely you will have larger areas, the parasitic capacitance will be more, and because the parasitic capacitance increases, now to respond to the increase in the parasitic capacitance, you have to increase CAC. Okay. So, there is a limit on this, you cannot overdo this. So, maybe you can think of going from 2 invert cascade of 2 MOSFETs, you can even try with a cascade of 3, but you know what you are losing now. Okay. So, what you lose is the area for CAC and more loading coming because of CP, but you save on the power which is consumed in the self biased inverter. That is what you do. Okay. So, surely not more than 2 or 3 cascades you can use in your CMOS clock buffers. Okay. So, this is the way in which we can actually buffer our CMOS clocks used with the oscillators. Okay. Thank you.